Let's talk a little bit more about A to D boards. A to D boards, or sometimes A to D. The A stands for analog, and the D stands for digital. And what we are using in the lab is an A to D board, taking the analog signal and transforming it to a digital signal. All right, so what's an analog signal? Well, an analog signal is any continuous time function. So if I can draw a clock, 12, 6, 3, and 9, did I do that right? Yeah, okay. And if we use an analog clock, it looks something like this. And maybe we even have a second hand going along here. That's continuous time function. That means these dials are continually moving, right? Continually moving. But we would recognize the position of these dials and be able to interpret that as a time. That's an analog signal. And you can find analog watches and analog clocks because and that's what they look like. Now, digital clock is a discrete time function. So here's my digital clock. And maybe I have a time of, maybe I used to 3 at the same time, 3, we'll call that 3:05. That's a discrete time function. It's a digital signal. 5, 6, 7, 8. There's nothing in between the 5 and the 6 on this digital signal. This is a continuous time function. There's always going to be, it's just always going to be going along here, and it's continuous. There's no break. Digital is discrete. What we are doing in our data collection is we are using analog to digital converters to take this continuous time function and convert it to a digital signal so we can work on it in the computer. That's all the A to D board does. Well, that's all it does, but it's actually pretty complicated. But the basis of it isn't too complicated. All right, but that's the concept of what an A to D board does. And you need an A to D board anytime you're recording any continuous time function. A ground reaction force is technically reaction to what the person's doing. The person is pushing on the ground continuously. That's an analog signal. The digital signal is the ground reaction force. Okay, that's the discrete time function that goes into the computer. Now, I guess we could say the ground reaction force is also continuous. And what we're going to do with our force platform is actually measure that continuous time function, and then our A to D board converts that continuous time ground reaction force to a digital signal. So I said it was digital. It's not really digital. It's digital once we get it to the computer. Okay, so now let's talk a little bit about how computers work and how A to D boards differ from each other. So computers talk to themselves in binary. And in order to understand binary, I think it's important to think back to what our number system is, the decimal system. It's a base 10 system, meaning if I take a number like 2,516, what is the base 10 system? Well, what this system does is it takes each of these numbers and multiplies it by a power of 10. This being the 0 position, the 1 position, the 2 and 3. Well, I say position. Well, what this is we take 6 times 10, which is the base of this decimal system, raised to the power of 0. 10 raised to the power of 0 is 1. So 6 times 10 is 1. 1, which is the next position, will be 10 raised to the first power. So 10 raised to the first power is 1. So 1 times 10 is 10. 5 times 10 to the second power, because now we're in this position here. And you got to remember, I call them positions because this is the 0, 10 raised to the 0. This is 10 raised to the 1. This is 10 raised to the second power, which is 100 times 5, that's 500. And 2 times 10 to the third power, which is 1,000, so that is 2,000. Then all we do is we add up all of these, and that is 2,510. Oh, sorry. You were screaming at the screen when I did that. That's 10 raised to the 0 power times 6 is 6, not 1. And I noticed that now because I'm adding this all up and it has to be the same number. So this obviously has to match that. This is the decimal system. That's how the decimal system works. Okay. Now, computers don't work in the decimal system. They work in the binary system or base 2. And they look at only 0 and 1. So they use only 0 and 1s. So now we need a counting system in binary. Well, it's the same thing, but now we can only use 0 and 1s. And in the decimal system, we can use numbers between 0 and 9. Remember, 0 to 9, that's 10 numbers. That's your decimal system. 10 values here. These 10 values can be used in any of these positions. And we multiply these 10 values by whatever power we're looking at in that position. Now notice I didn't put 10 here because that's two positions. That's 2 characters. So and here we have, if we count these, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because the 0 is considered a part of the decimal system as we do this. Okay. All right, so don't forget that. Now, in base 2, we have only 0 or 1 to use in our number system. We can't use 2, can't use 3, can't use 4, can't use any of them. You can only use 0 or 1. 0 or 1. So now we need to look at our binary number system, 1, 0. Let's use 3 positions. 101. Now that's not 101. We would not say that. We would say 101 in binary. 101 in a decimal system is a different numbering system. All right, so now let's figure out what this number represents. So now we do 1 times 2, because this is base 2 now, raised to the 0 power in this position right here. So 0. So 2 raised to the 0 power is 1. 1 times 1 is 1, which is what I was doing up here. 0 times 2 raised to the first power, because now we're in this position here. 2 raised to the first power is 2. 2 times 0 is 0. 1 times 2 raised to the second power, because now we're in this position. 2 raised to the second power is 4. 1 times 4 is 4. We add those all up and we get 5. So this number right here represents, in decimal, 5. Whoops, sorry. So we would actually use this set of codes, 3 digits, to represent the value 5. And we can do that for any number. So if I got, let's go to 1, 1, 1, 0, 1, 2. So now I've got 1 times 2 raised to the 0 power. That's going to be 1 times 1. 1 times 2 raised to the first power. So that's 2 times 1. 1 times 2 raised to the second power. That's 4. That's 4, 5, 6, 7. That's how we write 7 in binary. All right, that's 7. Now, we can just keep going. I mean, I go 0, 1, 0, using the same 3 digits or same 3 positions here. 0 times 2 raised to the 0, that's 0, that's 1. 1 times 2 raised to the 1, that's 2 times 1, that's 2. 0 times 2 raised to the second power, that's also 0. So that's how we would write the number 2. You can go through this and write your numbers between 0 and the highest number you'll get to is 7. But 0 is 0, 0, 0. 0 times 2 raised to 0, 0 times 2 raised to 1, 0 times 2 raised to 2, 0, 0, 0, 0. Okay. What's 1? 0, 0, 1. 2, 0, 1, 0. 3, 0, 1, 1. Okay. So you can count to 7 in binary using 3 positions. So if I want to get to a number higher than 7, I need another value here. Just like with our base 10, if I want to get higher than a number of 9999, I need another position here. All right. In the computer, we would call these bits. This is 1 bit, this is 2 bits, and this is 3 bits. These are 3 bits used to count to number 7. All right. Okay, so let's see. So an A to D board, see, I'm going to actually number these pages here. I will scan these afterwards and have them as a PDF on top of that. Okay, so an A to D board, when you buy an A to D board, you buy an A to D board based upon the number of bits. So we can buy a 3-bit A to D board. That means we can represent values between 1 and 7. We can buy maybe an 8-bit A to D board, or a 16-bit A to D board, or a 32-bit A to D board. What are we doing? We're actually increasing the number of values that we can represent based upon the number of bits in here. So let's see, we would, for the number of bits, we can take 2 raised to the 3rd power. That's 2 times 2 times 2, which is 8. That's how many values we can represent using a 3-bit A to D board. And remember, I already went over that. That's 1, 2, 3, 4, 5, 6, and 7. There's 8 values here. Notice the number 8 is not there, but that's okay because there's 8 values. 0, we count. That's 1, 2, 3, 4. Oops. There's a 2 in there. 1, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay. 8 values. 2 raised to the 8th power will tell us how many numbers we can count to, how hard we can count to, and that's 256. 2 raised to the 16. Oh, what's 2 raised to 16? 65, 536. I had to look at my notes. And 2 raised to the 32. Oh, I'm going to have to go to my calculator here. But this is telling us how high we can count. That's, I'm not going to write it down. That is 429,496,000. So I'm off by 1. You can do it. It's a lot. Okay. For an A to D board in your lab, you want as many bits as you can get. Okay. The cost of the A to D board is based upon the number of bits. This is a really low cost A to D board. This is a more expensive A to D board. At least it was in the past. I actually haven't priced them out in some time, but I've seen as high as 64-bit A to D boards. Okay. That's 2 raised to the 64th power. in terms of the number of values we can represent. This is all 0 and 1s, okay? It's all 0 and 1s. 8-bit, all 0 and 1s. 0, 1s, they're all 0 and 1s. 8-bit, 1, 2, 3, 4, 5, 6, 7, 8. Whatever that number is, that's 8 bits. That's 2 raised to the 0 power times 0, 1 raised to the 2, excuse me, 1 times 2 raised to the 1 power, 1 times 2 raised to the 3rd power, and so forth. 1 times 2 raised to the 7th power. Add up all those values, and that's the value that that number represents. There'd be 64 of these binary codes. Now, why use binary in a computer? Well, because what that means, or the basis of the computer, is an on-off switch. Either a switch is on or it's off. So it's either a 0 or a 1. And when you have a 0 or 1, or you have a switch that is on or off, now you can put all those switches together to now represent a value in the decimal system, base 10. All right, so that is the basis of A to D boards. And what else do I want to tell you on A to D boards? Let me look at my notes here. Well, let me switch screens, because there's one other part that is really important, and this is in the handbook. And I mentioned it in the Buyerware presentation about where you need to tell the data acquisition system what the range of the A to D board is. And typically the ranges are set for most data acquisitions, plus or minus 5 or plus or minus 10 volts. And that gives you the range of voltage that you can try to detect from your instruments. And most instruments stay within one of those two ranges. All right, so resolution is related to the number of voltage increments that we can make in the A to D board. So here's our 3-bit A to D board, and our 8 values, 1, 2, 3, 4, 5, 6, 7, 8, okay? 2 raised to the 3rd power. That's how many numbers we can represent. But instead of putting 0 through 7 here, I put in the range of voltage for the A to D board. And I set it in this example as a 10-volt range. So a plus or minus 5 volts. Okay, that's 10-volt range. Plus or minus 10 volts would be a 20-volt range. So -5 to +5 would be 10 volts. So now if I have a 3-bit A to D board, what that means is I can divide that voltage up into 8 evenly spaced increments. And I just divided it in by that. So I've got 0, 1.43, 2.86, all the way down to 10 volts. All right. Those are the voltages that if the A to D board sees 1.43 volts, it's going to use the binary code 001 to represent that voltage. If it sees 2.86, it's going to use 010. All right, now remember, we've got a continuous time function that we're trying to sample. We may not see, we may have a voltage that is not one of these values. So we may see, I used the example down here, 4.9 volts. 4.9 is not on this chart. So what does the A to D board do? It's either, and it depends on the system. It's either going to use 011 or it's going to use 100 to represent 4.9 volts. All right. So now you can see the resolution of a 3-bit A to D board is not very good. Now, I would use a 3-bit A to D board for something really robust, like maybe a switch, that a voltage, a synchronization switch that's turning on or off, where I'm looking for just a discrete value of maybe 5 volts. And it's either 5 volts or it's 0. Then I can detect that really easily using a 3-bit low cost A to D board. But if I really want to have a higher resolution, the ability to the ability to detect 4.9 volts, I need a to D board with more bits. okay? And then I would have finer resolutions. Now, thinking back to what I said, you can buy a 64-bit A to D board. I don't even know how many divisions that has. That has a lot, 2 raised to the 64th power. So all those, we would evenly increment the voltage from 0 to 10 or -5 to 5, whichever way you want to do it. Uh, and in even increments. And when we have a 64-bit A to D board, we have really small voltage increments. So now we're getting closer to being able to detect really fine changes in the continuous time function. It's still not perfect, but that's the A to D board. That's what the A to D board is doing, is it's converting your continuous time function to a discrete time function. And we do lose some information along the way. Our job when we collect data is to make sure we're using an appropriate A to D board for the signal that we are trying to detect. Okay, and I just said here, A to D units are voltages, which can be converted back to degrees. I went over that in the Bioware presentation, where your data acquisition system, for every instrument you plug in, you need to put in a conversion factor, being either degrees per volt, newtons per volt, or acceleration per volt, whatever it is. Or you got to check your data acquisition system. Sometimes they want volt per unit, sometimes they want unit per volt. Either way, you got to pay attention to it and put in the correct one, because obviously one's the inverse than the other. So here's just a conversion formula. A to D voltage times the units divided by the volt. Okay? So this is this is the conversion factor right here. And then you end up with units. So for example, if you have a conversion factor of 10 Gs per volt, if you see 2.5 volts, then you have an acceleration of 25 Gs. 10 times 2.5, the volts cancel, and I'm left with units of G. Okay, that's A to D board. Thanks.